Feedback control system, problem 1. Consider the differential equation d squared x over dt squared plus 3dx over dt plus 2x over f of x, where our f of x, function of x, is the input and is a function of the output x. If our function of x is equals to sine x, linearize the differential equation for small excursion, x is equals to 0 and x is equals to pi. So x is equals to 0, we let x is just equal to delta x plus 0, therefore, then we linearize this and we have delta double prime x plus 3 delta prime x plus 2 delta x is equals to sine, because our fx is equals to sine x, so our x is delta x plus 0, so that's it. But sine is equals to 0 plus, sine times 0 plus delta x is just equal to sine 0, and the derivative of sine x is equal to 0. Then our delta x is just equal to 0. Sine 0 is 0. When we input cos 0, we'll have 1. So delta x is just equals to delta x. Therefore, delta double prime x plus 3 delta squared x plus 2 delta x is equals to delta x. Then we equate this to 0. So we'll have 2 delta x minus delta x is just delta x, positive delta x. So we have delta double prime x plus 3 delta prime x plus delta x is equal to 0. Same step on B. We have the small excursion is equals to pi. We let x is equals to delta x plus pi. Therefore, delta double prime x plus 3 delta prime x plus 2 delta x is just equal to sine. Our x here is y2. This is not 2, it's only pi. So our x is equals to pi plus delta x. But our sine delta, we distribute this pi and delta x. So we have sine pi plus the derivative of sine x, we have cos x. So when our x is pi, we'll just have this delta x is equals to negative x. Therefore, our delta double prime x plus 3 delta prime x plus 2 delta x is just equals to negative delta x. And the final answer for B is when we add this, we add delta x, will have 3 delta x. So delta double prime x plus 3 delta prime x plus 3 delta x is equals to 0. Second question or the problem is, for each of the transfer function, find the locations of the poles and zeros, and then write the expression for the general form of the step response without solving the inverse Laplace. State the nature of each response: overdump, underdump, or critically dump, or so on and so forth. So A, transfer function is just equal to 10, open parenthesis, s plus 7, close, over s plus 10 times s plus 20. So to find the poles is from the denominator, so we'll just equate it to 0. So we have our s is negative 10. Same goes to s plus 20, we'll have our s negative 20, our poles. So this is our poles for A. Then our zeros is from the numerator, so we'll just have to equate this to 0. So it's just negative 7. So when we calculate the damping ratio of this given transfer function, our damping ratio is just equal to 4.47. Since 4.47 is greater than 1, so the response will be overdamp response. When you say overdamp response, it refers to a large amount of energy absorption of a system which inhibits the transient response from overshooting or oscillating about the steady state value for a step response. So overdamp response. B is our transfer function is equal to s plus 5 over s plus 10 squared. Then our poles will be from the denominator when we distribute this 2, so we have s plus 10 times s plus 10, so we'll have to equate that to 0. So we'll be having both negative 10 in second order response. So our s is negative 10 and negative 10, and we'll find the zeros from the numerator. So s plus 5 will equate that to 0, same. So s is equals to negative 5. So ct is equals to a plus b e raised to the power of negative 10 plus c t e to the power of negative 10. So when we calculate the damping ratio of this given transfer function, our damping ratio is equals to 1, and the response will be critically damped response, because critically damped response is the damping ratio is equals to 1. The last problem is for each pair of second order system that follow, find the location of the second order pair of poles. A, the given is percent overshoot and the settling time, which is our percent overshoot is just equals to 12% and our settling time is 0.6 seconds. And B, percent overshoot also is given, the peak time is given. So we have 10 and 5 seconds, and last is our settling time, we have 7 seconds and our peak time is 3 seconds. So to find the pose from A, we have given here percent overshoot and the settling time. To find the pose, we need to have this formula, the equation. Then we have negative damping ratio times natural frequency plus negative J times natural frequency square root of 1 minus damping ratio squared. To find this, we have to have this formula of the damping ratio. So we just need to input the percent overshoot, the 12 from the overshoot here. And we have 12 over 100, 12 over 100, and we'll find the damping ratio of 0.56. So we already find the damping ratio, we'll find the natural frequency, which is the formula 4 over damping ratio times settling time. We have 4, we already find the damping ratio, so 0.56 times 0.6 or settling time 0.6, then we'll have the natural frequency of 11.9. To find the pose, we need to plug in this damping ratio and natural frequency, so we'll find this pose negative 6.66 plus negative J 9.86. So move to B, just the same step but our natural frequency is different formula here. So percent overshoot is given 10 and our peak time is 5 seconds, so the pose also is the same and our damping ratio is just the same. You just need to input the 10 here and we'll have the damping ratio of 0.59. And our natural frequency, since peak time is given, not TS, we'll have this formula. So natural frequency is equals to pi over TP square root of 1 minus damping ratio squared. So we'll just need to input the TP here, which is 5. So our natural frequency is 0.78. And to have the pose, we need to input this 2, same, and we'll find the pose from B, which is negative 0.46 plus negative J 0.63. So last is C. No overshoot given, just the settling time and the peak time. So we just need to have this formula to equate. We just need to find the damping ratio times natural frequency. Since settling time is already found, we just need to input this to the calculator so that we'll find this. So 4 over 7 is just 0.57 or natural frequency times damping ratio. So we have that. You just need to input that into calculator directly. Shift solve. Then our natural frequency square root of 1 minus delta S is from this equation. We just need to input the peak time 3. So pi over 3 is just equals to 1.04. So you don't have to calculate the pose because diretso na, it's direct. Damping ratio times WN is just equals to 0.57 plus negative J WN square root of 1 minus damping ratio of 2 is equals to 1.04. So that's the pole for C. So that's the end of the problem given.